It's kind of wild, isn't it, how just a bit of code can, well, shut down a pipeline. Remember that 2021 ransomware attack? The U.S. gasoline one?
Oh, yeah.
Suddenly, getting gas was tricky, flights grounded. It really brought the digital world crashing into, physical reality.
It really did. And that event, um, as bad as it was, it just highlights why knowing how hacking works, even the attack methods,
hmm
it's not just for tech geeks anymore. It's like understanding the offense helps build better defense for everyone.
Exactly. And that's precisely what we're diving into today. We're looking at Ethical Hacking
Hmm.
by Dr. Daniel G. Graham from the University of Virginia.
Right.
He's not just a professor, though he is computer science, secure systems.
Yeah.
He also did time at Microsoft. So he knows his stuff.
Definitely has the credentials.
And this book, it's aimed at programmers, basically teaching them how to build hacking tools, do penetration testing, ethically, of course.
And what's interesting is Dr. Graham's take. He actually calls learning and encouraging ethical hacking imperative.
Imperative. Strong word.
It is. But when you think about how tied everything is to tech now, critical infrastructure, our daily lives, well, this kind of knowledge, it's maybe not just for the pros anymore.
Okay, so our goal today, using Dr. Graham's book as a guide, is to give you, the listener, a sort of shortcut into how this all works. We'll touch on setting up a practice lab, understanding things like cryptography, how exploits happen.
Giving you the core ideas without drowning you in, super technical details.
So where do we even start? What's the first step in this world?
Well, the book kicks off quite logically with the absolute need for a safe place to learn.
Right.
Because, as Dr. Graham points out straight away, it's flat out unethical and illegal to hack into machines that you don't own.
Makes sense. No messing with other people's stuff.
Exactly. So, step one is setting up your own virtual lab.
A digital sandbox, basically, where you can break things without real consequences.
Precisely. And the book gives you a really solid blueprint for one. It involves 5 virtual machines.
5. Okay, what are they?
So, what's neat about the setup he suggests is how each piece simulates a part of a real network. It's not just random VMs.
Okay, makes sense.
You've got a PeepSense router. That's your firewall.
Okay, your gatekeeper.
Then a Kali Linux desktop. That's loaded with all the hacking and testing tools. Your attack station, if you will.
Got it.
Then, critically, there's a target server called Metasploitable.
Metasploitable. Sounds like it's meant to be exploited?
It is. It's designed with known vulnerabilities. It's your practice target.
Okay.
And finally, a couple of Ubuntu desktops. These act like typical user machines, potential victims on the network.
Right, so you've got the attacker, the target, the regular users, and the firewall. A mini network.
Exactly. And the network setup itself is clever, too. Dr. Graham has you create 2 separate, isolated networks inside this virtual setup.
2 networks. Why 2?
Well, there's the main internal network sitting behind the PeepSense firewall, kind of like your home network.
Okay.
But then there's another private network tucked behind the vulnerable Metasploitable server.
Ah, okay. So, to get to that second network, you'd have to first hack the Metasploitable machine.
You got it. It simulates a more complex attack scenario, like an attacker gets a foothold, then tries to move deeper into the organization's network.
That's smart. Forces you to think beyond just the initial breach.
Exactly. It teaches lateral movement. The book starts you off just getting the main network running, but that second one comes into play later.
And if people actually want to build this, does he say where to get the bits and pieces?
Yep, core instructions. He points you to SourceForge for the Metasploitable VM version 2 is recommended, apparently easier to set up.
Okay.
And the Ubuntu ISO, just grab that from ubuntu.com. Standard stuff.
And the virtualization software, what holds it all together?
VirtualBox is what he uses in the examples. The book walks you through the basic settings, allocating RAM, maybe 2 gigs for Ubuntu, less for PepSense, setting up virtual hard disks, about 10 gigs each.
And the crucial part, connecting them.
Yeah, making sure each VM is attached to that internal network segment you create in VirtualBox. That's how they talk to each other. It's really step by step.
All right, so once you've got this digital playground set up,
Yeah.
what's next? How do you start understanding the vulnerabilities?
Well, the next logical step is looking at network traffic. How does data actually move around? And how can someone intercept it? Chapter 2 gets into ARP spoofing.
ARP spoofing. Okay, break that down. How does data usually travel on, say, my home network?
Okay, so inside your local network, like your house Wi-Fi, devices don't just shout into the void using IP addresses. They need a more specific address for the local delivery. That's the MC address.
MAC address, like a unique hardware ID for the network card.
Pretty much. Think of the IP address like the street name, but the MAC address is the specific house number on that street.
Hmm.
When your laptop wants to send something to your printer on the same network, it needs the printer's MAC address.
And how does it find that? Does it just know?
That's where ARP comes in, the Address Resolution Protocol. It's like your computer broadcasts a message saying, hey, who has the IP address 192.168.1.50? And the device with that IP replies, that's me. Here's my MAC address.
Okay, a discovery process. So how does spoofing mess that up?
Well, ARP spoofing involves sending out fake ARP replies. An attacker can basically lie and tell your computer, hey, I have the router's IP address, send traffic for the internet to my MC address. Or they can tell the router, hey, I have the target computer's IP address.
Whoa, so they trick devices into sending traffic through the attacker's machine.
Exactly. The attacker becomes the man in the middle. All the traffic between the victim and, say, the router flows through the attacker's computer.
And if that traffic isn't encrypted,
then the attacker can potentially read it. The book mentions using tools right there in the virtual lab to actually do this so you can see it work.
what kind of things could they see, like on a typical network?
Well, anything sent over plain HTTP websites, not using HTTPS.
Right.
Maybe some older email protocols if they aren't using TLS encryption. Sometimes even usernames and passwords if an application or website sends them unencrypted. It's less common now with HTTPS being widespread, but it still happens.
That's pretty concerning. But the book doesn't just have you use existing tools, does it? It encourages more.
Right. That's a key part of the learning process. Dr. Graham includes an exercise where he encourages you to write your own ARP spoofing tool.
In Python,
Yep, using a library called Scapy.
Scapy, what's special about that?
Scapy is incredibly powerful for network stuff in Python. It lets you build network packets from scratch, piece by piece, or dissect packets you capture. You can really manipulate things at a low level.
So building your own tool forces you to understand exactly how the attack works, not just clicking a button.
Precisely. It gives you that much deeper understanding, way beyond just running someone else's script.
Okay, so from intercepting traffic, the book moves into cryptography. Chapter 5. This is where things like ransomware come in, right? We hear about that constantly.
Yeah, ransomware is heavily reliant on cryptography. The chapter starts with the basics. First, symmetric cryptography.
Symmetric means same key.
Exactly. One secret key is used to both encrypt the data and decrypt it, like a simple padlock. Examples mentioned are things like one-time pads, which are theoretically perfect but hard to use in practice, and more common stuff like AES.
AES, that's the standard one, right? Advanced Encryption Standard.
That's the one.
Yeah.
Very strong, widely used, even recommended by the NSA.
Okay. Then there's the other kind, asymmetric.
Right, asymmetric cryptography. This uses two keys, a pair, a public key and a private key.
Public and private. How does that work?
So the public key can be shared with anyone. People use your public key to encrypt messages for you. But only you, with your secret private key, can decrypt those messages.
Ah, like a mailbox. Anyone can drop a letter in the slot, encrypt with public key, but only I have the key to open the box. Decrypt with private key.
That's a great analogy. RSA is a common algorithm for this.
So how does ransomware use these? Does it use one or the other?
It actually uses both in a hybrid approach, which is quite clever, really.
Okay. How so?
Well, encrypting huge files with asymmetric crypto is slow. Symmetric is much faster. So the ransomware generates a unique, random symmetric key for each victim machine.
Okay.
It uses that fast symmetric key to encrypt all your important files, documents, pictures, everything.
Right. That locks them up quickly.
But then how does the attacker control the decryption? They take that symmetric key, the key needed to unlock your files, and they encrypt that key using their public key.
Ah. So the symmetric key itself gets locked, and only the attacker's private key can unlock it.
Exactly. The encrypted files are useless without the symmetric key, and the symmetric key is useless because it's encrypted with the attacker's public key. The victim is stuck unless they get the attacker's private key, which of course the attacker holds for ransom.
Wow. That's efficient and
Yeah.
nasty.
It is. And again, to make this concrete, the book actually walks you through building a tiny, basic ransomware client in Python.
Building ransomware. Isn't that risky?
Well, it's extremely simplified. It's designed only to encrypt one specific file in the lab environment,
Yeah.
purely for educational demonstration.
Okay. Just to see the mechanism.
Right. You use a Python library called Fernet to generate the symmetric key, encrypt the file, then use a public key, provided in the example, to encrypt that symmetric key and save it. And then crucially, for the demo, it shows deleting the original symmetric key, mimicking how the attacker removes your ability to decrypt.
Gotcha. Understanding the enemy's tools.
For defensive purposes, absolutely.
All right, so we've covered setting up, sniffing traffic, locking data down. Part 4 of the book seems to shift into actively finding weaknesses. Chapter 9 talks about exploitation and 0 days.
Yeah, this is moving into the more proactive side of things, not just defending, but hunting for flaws. Dr. Graham mentions that while every bug is different, you do start to see patterns in how vulnerabilities occur.
And the ultimate prize in this hunt is the 0 day. What's that exactly?
A zero-day vulnerability is a flaw in software that nobody else knows about. Not the vendor, not the security community. 0 days since it became known.
So no patch exists for it.
Exactly. That makes them incredibly dangerous and valuable to attackers because they can be exploited before anyone knows how to defend against them.
The book uses a famous example, right? Heartbleed.
Yes, Heartbleed is a classic case study. It hit OpenSSL back in 2014, which is a library used everywhere for secure connections, like your HTTPS.
Okay, what was the actual flaw?
So OpenSSL had this feature called a heartbeat. It was just a way for one side of a secure connection to check if the other side was still alive. Kind of like saying, hey, I'm sending you 10 bytes of data, send them back so I know you're there.
Simple keep alive check.
Right. But the flaw was, what if you lied? What if you sent a heartbeat request saying, I'm sending you 60 kilobytes of data, but you actually only sent, say, 1 byte?
Uh-oh. What would the server do?
The vulnerable server wouldn't check properly. It would say, okay, you asked for 60 KB back, and it would grab the 1 byte you sent, plus the next 60 kilobytes or so of whatever happened to be in its memory right then, and send it all back to you.
Whoa, so it just leaks random chunks of its memory.
Exactly, up to 64 KB at a time. And that memory could contain anything. User login credentials that were being processed, session cookies, sensitive data, even the server's own private encryption keys sometimes.
That's terrifying. Leaking the private keys defeats the whole purpose of the encryption.
Precisely. It was a massive vulnerability. And the book doesn't just explain it. It gives you Python code to actually perform the Heartbleed attack against a vulnerable machine in your lab.
So you can see it happen.
Yeah. It shows setting up the connection, doing the initial TLS handshake, sending the client hello message.
That's the start of setting up a secure connection.
Right, where the client and server agree on encryption methods and stuff. The code shows sending that and then sending the malformed heartbeat request to trigger the memory leak. It even touches on details within that client hello message.
So after that specific famous exploit, the chapter talks about finding new bugs, right?
Okay.
Using fuzzing?
Yes, fuzzing. It's a really common technique for bug hunting. The basic idea is super simple. Just throw tons and tons of random garbage or malformed data at a program and see if it crashes or does something weird.
Just bombard it.
Pretty much. The thinking is that unexpected inputs might hit strange edge cases in the code that the developers didn't anticipate, potentially revealing a bug.
Does the book show how to do that?
Yeah, it includes a really simple Python fuzzer. It just generates random numbers and feeds them into a little test function to demonstrate the principle, just throwing random stuff at it.
But does random stuff work well? Sounds like you could be fuzzing forever.
That's the main drawback, Dr. Graham points out. Purely random fuzzing is often really inefficient. You might generate millions of inputs that don't do anything interesting before you stumble on one that triggers a bug. It's like searching in the dark.
A needle in a digital haystack. Are there smarter ways?
Oh, definitely. The book mentions more advanced fuzzers like AFL American Fuzzy Lop.
Catchy name.
It is. AFL is much smarter. It actually watches which parts of the program's code get executed by the inputs it generates. It uses that feedback to intelligently modify the inputs, trying to create new ones that explore different code paths. It's much more directed.
So it learns as it goes.
In a way, yes. It focuses its efforts where it's more likely to find something new. There's even a version for Python called Python AFL mentioned.
And even more advanced stuff beyond fuzzing.
Yeah, briefly. Dr. Graham touches on symbolic execution and dynamic symbolic execution, sometimes called concolic testing.
Symbolic execution. Sounds complex.
It is quite advanced. It involves like representing program inputs with symbolic variables instead of concrete values, and using math constraint solvers, theorem provers, to figure out what inputs could possibly lead the program down different execution paths, potentially finding paths that lead to errors. He gives a small example with variables and path conditions and mentions a tool called Anger for this kind of heavy-duty analysis.
Wow. Okay, so quite a journey then. From setting up a safe lab to sniffing traffic, understanding encryption and ransomware, finding flaws like Heartbleed, and then these advanced bug hunting techniques like fuzzing and symbolic execution.
Yeah, it covers a lot of ground. And as the book shows, Getting a handle on these concepts gives you really solid foundation in cybersecurity, whether you're trying to defend systems or, ethically test them.
It really provides that crucial baseline understanding of the tools and techniques involved.
Absolutely.
Which brings us to a final thought for you, our listener. We see cyber threats evolving constantly, getting more sophisticated. So, thinking about everything we've discussed, what role do you think ethical hacking really plays? How vital is it for proactively protecting our digital lives, our infrastructure?
It's a constant cat and mouse game, isn't it? Offense and defense.
It really is. Maybe this chat has sparked some interest. Perhaps you're thinking about setting up that virtual lab or maybe learning some Python for security. It's definitely a field that's not standing still. Understanding these basics is, well, a pretty important starting point.